Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. We have been looking at the input output system. In the previous lecture, we looked at the basics of an input output system, the basic interface which is used, which is the bus, and we talked about two different types of buses. We talked about a synchronous bus and we talked about an asynchronous bus. So, we looked at details of timing with respect to the synchronous bus. What we will do in today's lecture is we will look at asynchronous bus, how the timing and control is handled, and then we will look at how the commands are given, the input output commands are given, and how the data transfer takes place. So, as we said, in asynchronous bus, the data transfers are controlled by means of a handshake between the master and the slave. Remember the terms that we have used here, master and slave are the two devices which are talking using the bus. The one which is initiating the data transfer is the master, the one which is responding to it is the slave. Okay. So, your processor, if it initiates the transfer, becomes the master. If the IO device initiates the transfer, that becomes the master and the processor will become the slave. Okay. So, in general we refer to the two devices as master and slave, and when we talk of an asynchronous bus, we do not have a common clock as in the case of a synchronous bus. So, in the case of a synchronous bus, we have a common clock and every timing all timing is decided by with respect to that common clock. Okay. Whereas, here in an asynchronous bus, we do not have the common clock, and that common clock, instead of that common clock, what we actually have is two timing control signals, one called master ready and one called slave ready. Okay. So, instead of a common clock, we have these two timing signals, control lines, which are called as master ready and slave ready. So, let us see how using master ready and slave ready the data transfer can take place. Okay. So, when is this master ready signal asserted? Okay. What I mean by asserted is that it becomes active. So, the master ready signal is asserted by the master to indicate to the slave that it is ready to participate in a data transfer. Okay. And slave ready signal similarly is asserted by the slave in response to the master ready, and it indicates to the master that the slave is ready to participate in the data transfer. Okay. So, you can see why it is called as a handshake. Okay. So, master ready signal is like the master putting out its hand, and the slave ready signal is like the slave putting out its hand saying that I am also ready. Okay. That is the idea. So, let us look at how the entire series of operations will take place using the master ready signal and the slave ready signal. So, in addition to the master ready signal and slave ready signal, remember what we have are the address and command lines and the data lines. So, we need to understand how address and command is handled with respect to this master and slave ready signals. Okay. So, we will look at that. So, the first thing that will happen, okay, is that the master will first place the address and command information on the bus. Okay. You can see that is happening at time t naught, let us say. Okay. At time t naught, the address and command are placed on the bus. Once it does that, next step is the assertion of the master ready signal by the master. Okay. So, you can see that the master ready signal is asserted at T1, not at T0. Okay. This is because your once the address and command are placed, okay, it takes some time for that to stabilize. So, once it stabilizes, then the master asserts the master ready signal. Okay. Now, this ready signal is what master ready signal is what all the slaves will be looking for. So, when they find that the master ready signal is available, okay, and then they will look at the address and command and so on, decode, okay, and when they decode the address and they find that that particular slave is the one that is actually addressed, okay, and you can see that the slave now addressed and the slave becomes ready to give the data, the slave puts out a signal called the slave ready signal. Okay, you can see this over here. Okay, at time t2, the addressed slave places the data on the bus and asserts the slave ready signal. So, you can see that the data also is available at this time t2, and at that time the slave ready signal is given. Okay. So, you can see what we have here. So, master ready is given at time t1 after the address and command are placed, and after the master ready signal is given, decode and then identifying that the which device is to be accessed takes place, and that device actually gets the data and puts it on the bus. Okay. And at the time at which it puts it on the bus, at time t2, at that time the slave ready signal is given. Okay. Now, the slave ready signal arrives at the master, let us say at time t3. Okay. So, once the slave ready signal is seen by the master, now it can go ahead and read the data, right. So, you can see at t4, okay, now at once the at t3 you can see that the slave ready signal has arrived at the master, and the master now has removed its master ready signal. Okay. You can see that at t3 master ready signal goes down, okay, which means that the master has now taken the data that was available. Okay. Now, after the master ready signal goes down, okay, next thing that will happen is that the master now removes the address and command lines from the bus. Okay. Once it removes the address and command lines, then at time t5 you can see that the slave now receives the transition of the master ready signal from 1 to 0. Okay. So, remember this, master ready signal went from 1 to 0, but that has to be seen by the slave. Once it sees that transition from 1 to 0, that the master ready signal has been removed, then the slave ready signal also can be removed from the bus, that is the slave ready signal goes to a 0 state. When I say removed from the bus, what I mean here is, assuming that it is active in the high state and inactive in the low state, it is coming to the low state. Okay. So, you can see that happening here. So, the master ready signal goes down here, okay, which is seen by the slave, and in response to that it will remove the slave ready signal and remove the data from the bus. Okay. Now, you can see at the end of this time t5 your entire operation has been completed. Okay. So, we can see that both this master ready and slave ready, these are the two signals which are used to determine when data is available on the bus, when data can be taken in, and when the address is available on the bus, when the address can be decoded, and when the data is available on the bus and the data can be taken in. All these things are identified by means of these two signals, master ready and slave ready. So, when the master ready goes up, it indicates something, when the master ready goes down, it indicates something. Similarly, slave ready going up indicates that the slave is ready for the data transfer with the data. Slave ready going down indicates the completion of your IO transfer, of the data transfer. Okay. So, we start with the master ready going up and we end with the slave ready going down. Assertion of master ready to deassertion of the slave ready signal is the entire duration of your data transfer. Okay. So, this is how in an asynchronous bus the data transfer is handled. Okay. So, you can this is just to summarize what happens in this data transfer. So, in the asynchronous bus, the data transfer using the handshake protocol happens in the following manner. Step 1, master places the address and command information on the bus. Step 2, it asserts the master ready signal to indicate to the slaves that the address and command information has been placed on the bus. Step 3, all devices on the bus decode the address. Step 4, the addressed slave performs the required operation and informs the processor that it has done so by asserting the slave ready signal. Then the master removes all the signals from the bus once the slave ready is asserted. Then the slave ready signal is deasserted. Okay. These are the steps that that have to take place. Okay. So, if the operation is a read operation, the master will also strobe the data into its input buffer. Okay. That is something that will be done. So, if you do a quick comparison between the synchronous bus and the asynchronous bus, okay, there are certain advantages of the asynchronous and certain disadvantages as well. What is the advantage of the asynchronous bus? What it allows you to do is it eliminates the need for synchronization between the sender and the receiver, that is having a common clock and doing the synchronization with respect to that common clock, that is avoided when we go for an asynchronous bus. Second thing is you can easily accommodate for varying delays using the slave ready signal. So, you have a slower slave, it will put out the slave ready signal later. Okay. So, automatically you can accommodate for different timing with respect to or different delays of the different devices. So, that can be done easily with the asynchronous bus. The disadvantage is that the data transfer rate with full handshake is limited by 2 round trip delays. That is, what do you mean by 2 round trip delays? You need to have the master slave, the master signal ready signal going from one end to the other. Similarly, the slave ready signal going from one end to the other. Okay. So, whereas data transfers using a synchronous bus involve only 1 round trip delay, and therefore synchronous bus can achieve faster rates. Okay, this is something that we need to keep in mind. Okay, but of course we have buses which are used in today's processors. We have both synchronous transfers as well as asynchronous transfers. In some cases we go for synchronous transfers predominantly, in some cases it is asynchronous transfers predominantly. Okay. So, that is the way it is done. Okay. These are some examples of IO buses. We will look at details of these later in a later session perhaps, but these are examples of certain IO buses that are used. We have the FireWire bus, you have USB, the Universal Serial Bus, then you have PCI Express, Serial ATA, Serial Attached SCSI bus. Now, all these are different IO buses that have actually been designed and standardized. So, you can see that there are various details of these. What is the intended use, whether it is used as an internal bus or an external bus, and how many devices can be supported per channel using this kind of a bus, what is the data width, okay, and then what is the peak bandwidth, how much of data transfer can sustain, whether it is hot pluggable, that is whether you can plug in a device even when it is working or not, okay, that we call that as hot pluggable. Then what is the maximum length of the bus and what is the standard that is used for each of these buses. Okay. So, these are some details that we have in terms of IO buses. We will look at some of these details later. This is just to tell you that you have these kind of different IO buses that are designed and that are in vogue. Okay. Now, this is what a typical system, a PC based, I mean an 86 based PC system would look like, okay, with respect to the IO system. So, you can see you have the processor here, okay, and you will have a memory controller hub which is normally called as the north bridge, to which the memory will be connected, and then you will have your PCI bus, this is your IO bus, okay, to which the different IO controller hub will be connected, to which you have the PCI X bus and other things connected, to which you have the different disk devices, disks, keyboards, mouse, USB ports, all these things would be connected. Okay. So, this is called as a south bridge. So, north bridge and south bridge are two terms which are used to identify the memory controller hub and the IO controller hub. Okay. This is typically how things will look in inside of your PC. Okay. Now, we talked about the bus and how the actual transfer takes place with respect to the timing. Now, we also need to understand what kind of addresses are sent and how the commands are sent and so on, and how the two devices, the IO devices and the processor actually talk to each other. Okay. So, how is the management of IO actually done? Okay. So, IO management is normally mediated by the operating system. Okay. So, you have specific operating system routines which take care of the IO programming, and the way it is handled is that multiple programs would share different input output resources. So, the OS will have to take care of providing protection and scheduling and so on, which is why the OS handles it in a very unique manner. And the input output again can cause asynchronous interrupts. So, we need some mechanism like exceptions to handle that. So, that is also done with the help of the OS. Okay. And since directly accessing the IO devices would be very complicated, the OS provides abstractions for the programs to handle the IO devices. Okay. So, what kind of abstraction is provided? What is it that is actually done? Okay. So, to understand that, we need to know what is actually within the interface of an input or output device. So, you have these IO devices here, right, and we talked about an interface that is normally there. Okay, we said an IO controller or something which will be available, right, which connects to the actual device. So, what will be there within this controller actually, if you look at that, which is the IO interface part of the device, which is in turn connected to the bus. Okay. So, you can see that the bus has these address lines, data lines and control lines, right. So, the address lines will be connected to the address decoder. Remember, we talked about decoding the address and identifying that the particular device is being addressed. So, you will have a decoder here, and then there will be some control circuits, and then there will be data and status registers. So, the data lines will be connected to the data and status registers, control circuits will be connected to the control lines, okay, and it is these, the address decoder, control circuits and data and status registers, which are the ones which will act as the interface between the input device and the bus. Okay. So, when we talk about sending of writing data or reading data, it is basically writing data and reading data into its data and status registers. So, that is what will actually be done. We will take a look at these details after a short break. Welcome back after the break. So, we said that data is transferred to the IO devices by means of these data and status registers. So, normally what we talk about is we refer to these data that is transferred as commands, as IO commands. Okay. So, so in fact, when we talk of data and status registers here, we also refer to these data registers as command registers. Okay. So, we have command registers which will cause the device to do something, okay. And then we have these status registers which will indicate what the device is doing and the occurrence of errors. So, you can see that if an error has occurred on a particular input or output device, it would have set some bit in the status register. So, the processor can always read the status register and find out if something has gone wrong and what has gone wrong. Okay. And the data registers that we talked about, right. So, the data registers are the one which are actually used to transfer the data to the device. So, you would have write registers and read registers. Normally, there are separate registers, write registers and read registers if it is an input come output device. If it is an input only device or an output only device, then you will have only one set of registers, either read or write registers. Okay. So, you can see that you will have this address decoder for doing the decoding, control circuits which will take care of handling the different commands, okay, and it will talk to the, and of course, you will have these data, command and status registers which will handle the interface between the devices and the processor. Okay. So, now the question is, how do I address these registers? Okay, that is the next thing. So, we have said that there is an address decoder, so which will look at the address and decode it and identify that it is this particular device which is being addressed. That is not a problem. Okay. What we need to understand is where exactly are these addresses specified. Okay. We know that memory, there is a set of addresses given for memory, but what about IO addresses? Do we have separate addresses for IO, or do we have to use a part of the memory addresses itself as IO addresses as well? Okay. Both these options are available. You can either have separate addresses for IO, or you can have a part of the memory addresses, that is, we have some addresses, a set of memory address space that is available. A part of the memory address space can be used for the IO operations. Okay. So, we talk about what we call as IO register mapping or IO address mapping, and we talk about something called memory mapped input output or IO mapped input output. Okay. So, in memory mapped IO, these registers, the IO registers that we have, are addressed in the same space as the memory. Okay. And the address decoder can distinguish between whether it is a memory or a IO address by looking at the address, because there are only some specific addresses which are assigned for IO. So, by looking at that address, the decoder can identify that it is an IO address. Okay. And the OS will use address translation mechanism to make them only accessible to the kernel. That is, remember, the IO devices, if they are part of the memory address space, should not be tampered with by any program. Okay, because then if it is a memory address, if some program writes into that memory address and it actually goes and writes into your IO device, that can cause havoc. So, that should not be allowed. So, normally what is done is the OS will use the address translation mechanism that it has to make sure that these addresses are available only to the kernel mode of operation, to accessible only to the kernel. So, accessible only in a supervisor mode of operation. Okay. So, with this kind of a setup, you can have a memory mapped IO and have the registers occupying the same address space as the memory itself. This is one option that we have. Second option is provide for an IO mapped situation where we have specific IO instructions, that is, there are separate instructions which are available to access input output registers. Okay. Remember, when we talked about different types of instructions, we have talked about IO instructions and we talked about something called input instruction, in instruction, out instruction and so on. These are the instructions we are referring to over here now. So, these kind of special instructions, okay, can be used to access the input output devices. Okay. Of course, these instructions again can be executed only in kernel mode. Okay. Some processors like the x86 support this kind of a separate instructions for IO. Okay. So, these are the two options that we have. So, let us look at what will happen in a case of memory mapped IO and in the case of IO mapped IO. So, look at this. So, what we have here is the CPU is there, you can have a separate memory bus, okay, and an independent IO bus. Okay. So, in this case, this is the example of separate IO instructions, that is the IO mapped IO. So, what will happen here, when if it is a memory operation, it goes to the memory bus and you can access the memory. If it is an IO operation, then there is a separate IO bus that can be used, okay. And this IO bus is the one that is connected to the interface, different peripherals, okay, and they are connected by means of this interface to this bus, okay. These are our interfaces for the IO devices. This is an option that we can have. So, if it is an input output, it will come out onto this IO bus. This is a possibility. Second possibility is you could also have a common memory and IO bus, right. This is something which we have already seen, okay. For instance, you will have the common bus to which memory as well as the different IO interfaces are connected, but there may be some special signals here which indicate whether it is a memory address that is being put out or an IO address that is being put out. This is another option that we have, okay. In which case you will you can still have independent IO address space, but there will be a special line which indicates whether it is a memory address or a IO address, but you have a common bus that is shared by the memory devices and the IO devices. Now, if it is a memory mapped IO, then typically it is this scenario, this kind of a configuration that will be used, that is you will have a common address bus and it will be used both by memory as well as by the IO devices, and after all it is a common address space. So, both will share the same address bus. So, both these are two different configurations which can be used to support the these two configurations, memory mapped IO and IO mapped IO. So, if you have a memory mapped IO, that is we said there is single memory and IO bus, no separate IO instructions, okay. In this case what you would normally have, the way the address space will be divided is, you normally have ROM at the highest address or the starting at one end of the address space, and then you will have your RAM space, and the other end of the address space will be reserved for input output operations. So, this is the way memory mapping can be done, right. So, once we understand how the memory mapping is done and how the addresses are assigned and so on, next thing is we need to understand how the data transfer actually can take place, okay. So, under what control will the data transfer take place, or under whose control will the data transfer take place? Is it under the control of the processor that the transfer will take place, or is it under the control of the device that the transfer will take place, okay. So, let us look at what are the challenges that we normally have with respect to data transfer, okay. So, depending on the challenges we can decide on who should initiate the transfer and so on, okay. So, what are the challenges that we have? One of the challenges is the rate of transfer to and from IO devices is slower than the speed of the processor, okay. This is something that we need to keep in mind. The rate of transfer to and from IO devices is slower than the speed of the processor, okay. So, this means we need to have mechanisms to synchronize data transfers between them, okay. So, this is the first challenge that we need to keep in mind, that there is a difference in speed, okay. So, now you have one option which is to go in for a program controlled IO, where the processor will repeatedly monitor a status flag to achieve the necessary synchronization, okay, because this IO device is slower. So, how do I know when the IO device has become ready? You can have it done by the processor or have a program. What is it that the program will do? It will keep every now and then there will be some instructions in the program which will go and read some status flag in the device to see whether data is ready or not, okay. This is one operation that can be done, okay. Remember, this is different from our slave ready signal that we were talking about. There the transfer has been initiated and it is for the actual transfer of data that we are talking about. Here what we are talking about is we do not know whether that is data available with the input output device for it to be read by the processor or not. So, first of all that information has to be given to the processor. To find that, we are having this status signal here. So, there has to be an IO operation operation taking place to go and find out whether there is data available or not, okay. That is what we are talking about over here, okay. So, that can be done under the control of the processor. So, the processor will repeatedly monitor a status flag to achieve the necessary synchronization. So, what we say here is we call this as a polling mode of operation, where the processor is polling the IO device, okay. It goes and checks with each and every device, are you ready and so on. So, it is called as polling the IO device. This is one method. As you can see, this normally is a slow way of doing things. So, there are better mechanisms than this which can be used for faster synchronization and faster data transfers. Okay. The two other mechanisms that are used are interrupts and direct memory access. Okay. So, interrupt essentially is that when the data becomes available, or when the IO device becomes ready with the data transfer, it will send a special signal called an interrupt to the processor, and then the processor can come and read the data. Okay, that is called as an interrupt based IO transfer. The other is a direct memory access, wherein we are not even okay, again you will again it is the responsibility of the device to do the data transfer, but here the transfer of data itself does not require the intervention of the processor entirely. It can the data can be transferred directly into the address space, into the memory from the IO device, okay, by the IO device itself. So, we call it as a direct memory access. This again allows for some faster data transfers. We will look at details of direct memory access later. Okay. So, let us first look at what happens in the polling mode or the program controlled mode. So, what happens in the polling mode is that periodically the processor will check the IO status register. If the device is ready, it will do the operation. If error, then it will take an action. Okay. If it is ready, it will do the operation. If it is not ready, it is obviously going to come back and check again. But if it identifies there is some error, some other error, it has to take the necessary action. Okay. This is what we will do. This kind of a polling mode is suitable when you have small or low performance real time embedded systems. That is, you have limited number of devices that you are polling. Okay. In those cases, this kind of an option can be used. So, this can be used when you have predictable, when you need predictable timing, and the hardware cost is low because you do not have any special hardware to do any of these interrupt or any such operations, right. So, the generally the cost of the hardware can be maintained as a low cost hardware. Okay. But the only problem is that it will waste a lot of CPU time because this you have to execute instructions to come and check this again and again, right. So, it is wasteful of the CPU time. Okay. So, for instance, this is how programming polling will take place. Okay. So, you have CPU, memory, the IO controller where the control signal or the status register will be present, and then you have this device. Okay. So, what is going to happen? The process is going to be always in a busy wait loop. Okay. Keep checking, is the data ready? Yes, then it can go and read the data. No, then what will it do? It will go back and come back to check whether the data is ready again. So, if the data is not ready, it is in a busy wait loop. So, you can see that it is not efficient to use the CPU unless the device is really fast. Okay. So, if the data is ready, then you will go read the data or store data, whatever you could do, and then once you are done, okay, yes, then you complete, otherwise if it is no, then again you go back and check whether the data is ready and so on. Okay. This kind of a checking again and again, if it were in a busy wait loop, it is absolutely wasteful of the processor time. So, what we normally do if you are using polling is that if there is some other computational intensive code that needs to be done, you execute some computational intensive code and periodically come back and check whether the data is ready. Okay. So, in those cases you can make use of this kind of a polling based technique. Yeah. So, we can see that this kind of a polling based technique can be very slow, which is why we have better techniques like the interrupt based techniques and so on, which we will look at in later classes. So, to summarize, what we have covered today is we have looked at asynchronous buses and how the data transfer takes place with the help of master ready and slave ready signals. We looked at what is there in the IO interface, the address decoders, command status and data registers, which actually are the ones that are used by the processor to talk to the devices. And we looked at addressing IO, whether we used memory mapped addressing or we do have a separate IO address space, which is called as IO mapped IO. And then we talked about how data transfer is done using polling. So, questions to review today's content. Question number 1, list the steps involved for a read and a write operation in an asynchronous bus. Question number 2, what is memory mapped IO? Question number 3, name 2 IO bus standards you have come across. Question number 4, how does the polling mode of data transfer work? Question number 5, why would polling be better suited for embedded applications? Thank you.